Hello everybody, this is Werner Reinhardt speaking, and I would like to welcome you to the second lecture of this course, Electrodynamics for ICE students, this semester term. And I will proceed with the introduction of our electrostatics basic considerations. Last time we ended with the equation for the Coulomb's law, which was of the form, it was in the section 1.1 named the introduction. And we had outgoing from some two charges in a coordinate system Q1. So you have it already in your script from the last lecture. Q1 and Q2, two point charges, and some coordinate system with the origin somewhere x, y, and z, and the vectors, the vector R1 pointing to the location of the first vector of the first charge amount Q1 and respectively for Q2. And we have the separation vector pointing from 1 to 2, and we have the unit vector, the E12, in this case also the length of 1, and we have E12 equals to R12 over the magnitude of the vector R12 in magnitude signs. So it is called the R12 is called the separation vector, and last time I mentioned two different notations. One was one is a point of interest, R2 may be a field point or whatever. These are local coordinate vectors stemming from the origin of an arbitrary coordinate system. And we have the separation vector. If we have R1 and R2, then we always have to fulfill the triangle R1 plus, we have to do this loop, R1 plus R12 equals to R2. So you can reach to this point Q2 directly via R2 or via R1 plus R12. This is this equation, and we end up with R12, the separation vector, equals to R2 minus R1. It is quite simple, and the magnitude of this vector is the square root of the components of the three coordinates of the vector. So, which means R12, the magnitude is also written in R12 without any vector sign. So, and for this we can develop some force acting on the F12 on the force on the charge 2 to become, this was Coulomb said F, the force pointing from 1 to 2 equals to Q1 Q2 over 4 pi epsilon 0 times R12 as a vector over the magnitude of R12 powers 3. This is the same like Q1 Q2 over 4 pi epsilon 0, the unit vector E12 over the vector magnitude of R12, but in square. So we also took advantage of this relation for this expression here. So here we have ended, and we said that the actio equals to reactio. This was the first, was the third Newton's law, and we finished the last lecture at this point. So I would like to introduce another nomenclature for the source and field point vectors. RS may be a source point vector, and also R prime is a source point vector. So this I did not mention last time, and I added it this day. So we can write also in the location vector, the field point vector R remains always the same, the field point vector. So the separation vector may be field point or R in general. So we have R minus R prime is also the same like R1, 2. If R1 and R2 are the points as sketched here below. So coming to the next, to the superposition of forces. So if we have more than one or more than two charges in space, then we have to do some superposition in vectorial manner. So let's discuss a case A. If we have three amounts of charges, Q1, Q2 and Q3. Case A, for this we can say, okay, Q1 is present and Q2 is present, and Q3 is located at infinity. So then we have some charge Q1, and we are always examining the forces acting on this Q1. Q2 is somewhere placed, let's say at this position, Q2. Then we have some line of connection between them, and also the tangent again for this. Then we have some force F pointing from 2 up to 1, F21, and we have some unit vector, direction unit vector pointing from 2 to 1, E21. And the force may be described as F21 equals to Q1 Q2 over 4 pi epsilon 0 times E21, the unit direction vector, over the magnitude of the vector in square. So, case B. We have again our charge Q. Oh, the wrong color. Q1. And maybe the charge Q3. Okay. We have to write Q1 and Q3 are present. And Q2 is at infinity. Then we have in some other location, maybe horizontally situated, the charge Q3, or the amount of charges Q3, and we have a force acting on Q1, which is F pointing from 3 to 1, F3, 1, with the unit direction vector E3, 1. So we can write also for this case F21 equals to Q1 Q3 over 4 pi epsilon 0 times E31 over R31 magnitude square. So, and superposition means, in the case C, Q1, Q2 and Q3 are present. This means we have to summarize all effects acting on Q1 by a geometrical addition, which means a vectorial addition. We had Q2 and horizontally Q3 situated. And we had the vectors F2, 1 and the force F3, 1 from charge 3 Q3 to 1. So we have to superpose the vectors to get vectorial addition, the whole force acting on this charge Q1. This may be F1. So this means F1 equals to F3, 1, F2, 1 plus F3, 1. Which is Q1 over 4 pi epsilon 0. This is always the same for all parts of the forces. Then we have from the second force Q2 E2, 1 over R2, 1 square plus Q3 E3, 1 over R3, 1 square, and the square bracket is closed. So this is superposition, a vectorial addition. Of the effects of the forces. So it is quite wrong to add only the magnitudes of the forces to the whole force, because this may cancel out if Q1 and Q3 are in the same line as Q1, Q3, and may be of opposite sign. Maybe there's something 0 in between. So we are coming to the electric field, subsection 1.2, the electric field. That's the letter E, as we already know from the basic lectures. The total force acting on a charge Q and it's always meant an amount of charges Q is F equals to the sum of all j equals running from 1 to uppercase n of q times qj over 4 pi epsilon 0 ej and rj square. So where rj is the separation vector, and we know it already. So this means that we have always one constant q. This is the charge q, which is considered on which the force is acting. We can divide this equation formally by this charge q. And we have F over Q. And this is a new vector because it has another unit, but it points in the same direction as F if Q has the same sign. Then we have the vector E, the electric field E, equals to the sum of all j equals from running from 1 up to uppercase n of qj ej over 4 pi epsilon 0 rj square. So, and n is the number of amount of charges. This is without Q. Because Q is considered, which is acting all around, is acting on this Q. So we can also say this sketch it in a coordinate system, maybe in such a way, x, y, z, and we have some amount of charges, q1, q2, 3, 4, 5, j. So q1, q2 up to qj or n, whatever. And if we pick out one charge, then we have the source point vector r prime, for example, and we have some field point vector. The field point vector may be somewhere of interest where this charge q is situated. This may be the field point vector r, and the charge q is situated there. And we have for all j running from 1 to n established this separation vector r minus r j prime. This is the source point vector and this is the field point vector. This is the separation vector. For the j vector, and the field point is always the same. So it is quite simple, but we have to discuss it because sometimes some students are confused about that. Now, often only one amount of charges is Q1 is given. Then the origin of the coordinate system can be moved to the location of Q1. So this means if we have our coordinate, our Q1, and we have only one charge Q1 or amount of charges, then we can move the coordinate system into this, the origin of this into this coordinate system, x, y, and z, to the location of the charge Q1 z. So this means the source point vector equals to 0. So it makes more all a bit simple, because then we have a very simple mathematics. If we have some location point, this is the field point R, and in this point we can, the field point, I will abbreviate this with FP, field point, and from this we can say, okay, our electric field has only a radial component depending on the radius r, because we can write the relation E depending on the radius r equals to Q1, this is the amount of charges, over 4 pi epsilon 0 times E in radial direction over the radius r square. So, or can also be written in this form: Q over 4 pi epsilon 0 times R over R power 3. Now, and it's quite simple, because it is like a spherical coordinate system. With only the radial component is of interest. It is more or less a radially symmetric field pattern. So, what about the validity of this electric field E, the magnitude as well as the force? As we learned, proportional to 1 over r square, over the distance from the charge, from the given charge. So for radius greater than 10 powers minus 16 up to 10 powers minus 17 meters. For small it is valid. For smaller, you should keep in mind that the diameter of atoms is in the vicinity of 10 10 powers minus 10 meters, so in angstrom meters. For smaller let's say smaller than 10 powers minus 16 to 10 powers minus 17, then we have a quantum electrodynamics. And the upper bounds for the validity of this relation is for radius up to r greater than 10 powers 8 meter. It's a measure. This could be shown in an experiment. The measurements of the Jupiter fields, Jupiter fields by the space probe Pioneer 10. The mission of this was between 1972 and up to 2003. This was the mission of Pioneer 10, and they measured with this Pioneer, with this field space probe, the validity of the upper limit up to now. Maybe they are larger. The law will hold for larger distances, but up to now there's no experiments done which could establish this assumption. 1.3. The next one is the discussion about continuous charge distributions. And we'll start with volume charges. Volume charges, in the formula we have rho, Greek rho, in ampere seconds per cubic meters. It is called a volume charge density. So we have a coordinate system somewhere. X, Y, Z. And we have somewhere some volume. This may be the volume omega. Inside this volume omega we have an infinitesimal small cube. This may be d omega prime. And we have also this, because it's a source volume, primed nomenclature about, and we have some charges inside this infinitesimal small cube. And for any cube, for any charge within this cube, we have delta Q is the sum of J equal running from 1 up to n Qj charges containing in this sum of unit charges. in this volume delta omega. And delta omega prime equals to delta x prime, delta y prime, delta z prime, if it is in coordinates of Cartesian description. Then we have for any point, we have for any charge, we have some prime vector, some source point vector, and for a considered field point, we have somewhere maybe this is our field point, and the field point vector may be the vector r. And we have the separation vector, it's always the same. R minus r prime is our separation vector. For this we can rewrite our rho, the charge, volume charge density, depending on the coordinate of the source points r prime, equals to the sum of all j running from 1 to n qj over d omega prime. And this is because this sum is delta q dq over d omega prime. So, and from this we can extract a relation that in general form delta q equals to the charge volume density depending on r prime times d omega general. Then we have all charges contained in this delta omega. And if we will evaluate the electric field in this field point, then we have to do a summary of over all charges. And luckily we can superpose it, and superposing means it's an addition, a geometric addition of all effects of all charges containing in this omega prime. This means we can make a summation, and summation in infinitesimal small units is always an integral over the source volume omega prime of the charge density. This may be a regular distribution or a non-regular one, doesn't matter, over d omega prime, and we have the separation vector r minus r prime power 3 if we write here the r minus r prime as a vector. So this is the electric field due to superposition possible for our electric field in an arbitrary field point. We take advantage of this superposition, which is possible and allowed. I should mention that we should memorize this with a star, because later I will remember, switch back to this relation we need it a bit later. The next one is the surface charge. Another form of continuous charges is one dimension lower. It is surface charges. On some surfaces may be some surface charge density sigma in ampere seconds per square meter, one dimension lower. It's a surface charge density. Then we have the following relation. We have some surface in some way arbitrarily formed. This may be our source domain gamma prime, and inside this we have some infinitesimal small delta gamma prime, and a given sigma, a distribution of the charges along the surface is given, and in any field point we have to establish a relation. This is the field point with the separation vector r minus r prime. We have to evaluate the form to find the electric field for this case as 1 over 4 pi epsilon 0 times the integral, again a summation of all charges contained in the surface gamma prime of the given charge, surface charge density depending on the source vector times d gamma prime over the separation vector, always the same, r minus r prime square, and e, or let's have it's a better writing, 3 times r minus r prime as a vector. So it's nothing new. And the third form is a line charge. This may be spanned with, written with a tau, Greek letter tau of ampere seconds per meter. So this is a line charge density. This line charge density may be given in such a way. We have some line along this source domain, it is L prime, and along this there is some delta L prime, and for any field point we have some separation vector r minus r prime. This is the separation vector, and we can establish the electric field to become E equals to 1 over 4 pi epsilon 0 times the summation over the whole source domain, this is L prime, times the integrand tau depending on the radius r prime of TL, must summarize prime, over the separation vector r minus r prime power 3 times the vector r minus r prime. So these are continuously distributed charges in some constructions, maybe along a line, a surface, or in a volume. So we will proceed with our next subchapter. This is the consideration of Gauss law in electrostatics. 1.4. This is Gauss law in electrostatics. Gauss law in electrostatics. Supposing we have a volume, an electromagnetic field potato, some arbitrary shaped volume. Inside this volume omega, there are some charges Q1, Q2, Q3, and so on up to Qj. And we have n charges, n point charges inside omega. Then we have the volume may be defined by some closed surface gamma. And we have on any point on the surface some outer unit normal infinitesimal surface element delta gamma pointing out of the volume. And we can say the closed surface gamma always defines a volume. Omega. By sure. So we can now look for the flux. It is given by psi equals to the closed surface integral over gamma of the electric field E dot d gamma. So we have to, we can also take advantage of superposition. This means we have to summarize over the whole surface gamma, closed surface gamma of E1 superposition plus E2 plus En dot d gamma. This is summation of gamma of E1 dot d gamma plus the integral of gamma of E2 dot d gamma plus the integral of the nth En dot d gamma. So in this we will evaluate for example for the first integral to show something. This is the first for Q1 to establish the integral E1 dot d gamma over the closed surface gamma. I will do it on the next page because we have to do some sketch on it. We have some coordinate z, x, y, and we have located our charge Q1 in the origin of this coordinate system, so we can consider our surface integral in spherical coordinates. This is 1/8 of the whole sphere, and we have to consider only one small part of it. Maybe this is an infinitesimal small angle delta phi, and we have some wedge in this way, and we have some on the surface, we have some small delta gamma, which is always pointing in radial direction. This may be the radius, and the electric field in radial direction. E in 1 has only a radial component, and also the surface outer unit vector d gamma on any point in radial direction. So we have to evaluate the integral over gamma of E1 dot d gamma. So what's d gamma? And I will make a zoom of this wedge there. of this volumic wedge, and I have in grade I have the Z component, then I have this line of the radius R, this may be this line, and the other line was this. So this is this wedge, and I have the surface element pointing in radial direction. The radius R. I will write it this way. So then we have different kinds of parameters. This is delta phi, and the angle between the x-axis and this wedge may be phi, and the angle from the north pole, from the z-coordinate, may be delta. Then we have the projection of this, if we take a parallel. Then we have this radius there. This is R times the sinus of delta. So we can construct our surface element. This may be R times d delta, this part as well as this part, and the other one, this part, is R sinus delta times delta phi. And the direction of this vector is in radial direction. This is in radial direction. So we can establish this delta gamma to become R d theta times R sinus theta d phi, which is in radial direction, which is R square sinus theta d phi d theta. Now for this we can evaluate our integral which we are looking for. We can say, okay, our integral over the closed surface gamma of E1 dot d gamma equals to, we know from the point charge Q1 that we have Q1 over 4 pi epsilon 0 times the 1 over r square times the direction of the electric field is in radial direction. This may be, this is E1 depending on the radius r dot delta gamma, and delta gamma equals to, ER is missing here, ER times r square sinus theta d phi d theta. Now we can take advantage of our knowledge of vectors. We know this is identical to 1. The unit vector dot produced in the same vector leads to the length of the unit vector 1. So we can also cancel out r square, and it remains, we have to integrate over delta phi and over delta theta. So we have to define our bounds of the integral to establish a closed integral volume, a closed surface. So which means we can let run phi from 0 to 2 pi. This is the azimudal angle, but we have also to establish the integral over the space angle phi of theta equals from 0 to pi, from 0 to the south pole. Then we have the whole wedge, and that may be summarized along all 2 pi phi elements. So we get q1 over 4 pi epsilon 0 times, and if we integrate once delta phi sinus theta times delta theta delta phi, we get 4 pi, and we cancel out this 4 pi, and we get as a result q1 over epsilon 0. So this is a very convenient relation. We can do it for all n elements, in this formula to get in general we get for the integral of E over the closed surface gamma E1 dot d gamma plus integral over gamma of E2 dot d gamma plus the integral closed integral of over gamma of En dot d gamma, we get 1 over epsilon 0 of q1 plus 1 over epsilon of q2 plus 1 over epsilon of qn. And we can write this in a general form as the closed surface of over gamma of E dot dn d gamma equals to 1 over epsilon 0 times the sum of j running from 1 to n point charges containing in this volume qj, and this is 1 over epsilon 0 times the enclosed charges in this closed surface defining the volume omega. This is called the Gauss law in integral form. Now, by introducing the displacement vector d to be epsilon 0 times E for free space, it follows that the closed integral of d dot d gamma over the closed surface gamma equals to q enclosed, which is a relation you already know from the basic lecture. So let's keep in mind this relation and switch to a next page, applying the divergence theorem to this relation d dot d gamma equals to q enclosed over the closed surface gamma. Now applying the divergence theorem, we already know, then we can say, okay, our closed surface gamma and the integral of d dot d gamma can be changed to a volumic integral of the divergence of this vector d omega. So this is the divergence theorem, which we already discussed in the first lecture. This is Q enclosed. So, and now we can remember that we had a relation with a star previously, which meant that Q was the sum of rho dot d omega in a general form. This can be substituted in this Q enclosed, and we have the divergence of the vector d omega over the omega equals to Q enclosed, and this may be expressed by the volumic charge density rho d omega over omega. Now we have a relation where we have some integrand and the same delta omega. This holds for any volume arbitrary volume omega if the integrands are equal. This equality is very, very important. So this means the integrands must equal each other, and this leads to the divergence of d equals to the volumic charge density rho, or in other expression, the divergence taken of d equals to rho. This is the same as the divergence of E equals to rho over epsilon 0 for free space, because epsilon 0 is a constant. And this relation's divergence of D equals to rho is called the Gauss law in differential form. Differential form is obvious because we have to build the divergence of a vector, and divergence also always contains derivatives. And later we will learn that this is also called the third Maxwell equation. So I think this is enough for today, and I say thank you for your attention and wish you a nice week. I have to announce that on Wednesday in the afternoon there will be no lecture, no exercises given. Thank you very much. See you and keep healthy. Bye bye.